Good afternoon, my dear students. In the last class, we have discussed about what is the electric field, electric intensity, and magnetic potential, isn't it? The next is the derivation of the electric intensity at any point due to a dipole on the axial line and the equatorial line of a dipole. Those two derivations also we have discussed in the last class. Now, today we are going to discuss in detail about the magnetic potential and the derivation of the formula for magnetic potential at any point on the axial line of a dipole and equatorial line of a dipole. Now, again, just to recall the definition of the magnetic potential. Yesterday we have discussed that magnetic potential at any point in the magnetic field, magnetic potential at any point in the magnetic field, it is equal to the amount of work done in bringing a unit north pole, or you can call it as a positive pole, unit north pole from infinity to the point against the field. Now again repeat, magnetic potential at any point in the magnetic field, it is equal to the amount of work done in bringing a unit north pole from infinity to the point against the field. This is the basic definition. Now here, in the lower classes, that is in PUC, you have studied that suppose if this is a magnetic pole of strength, what is the M, and P is the point which is at a distance of D from the pole. According to the definition, the potential at the point P is equal to the amount of work done. If you consider this is a point of infinity, isn't it? Then even this also I made it clear that which point will be taken as point of infinity means it is the point, isn't it, from the pole where the magnetic field is zero. Suppose if this is the what is the magnetic pole, and at this point if the magnetic field is zero, then this point will be taken as a point of infinity. According to the definition, if this is a magnetic pole, and at this point, what is the magnetic potential means? According to the definition, it is equal to the amount of work done in bringing, isn't it, a unit north pole from infinity to the point against the field. Against the field is nothing but if the magnetic field is in this direction, isn't it? You are bringing opposite to that. Now that is the definition of the magnetic potential. And in the UC, then already you have derived the formula for the magnetic potential at any point due to a magnetic pole. That formula is that magnetic potential V is equal to, formula is mu naught divided by 4 pi, isn't it? Then M divided by what it is, this as a small m divided by what it is, a D, isn't it? What is this M? M is nothing but it is the strength of the pole, and D is the distance of the point of the pole. Now see, this is the formula for what? This is the formula for the magnetic potential at any point due to a magnetic pole. Isn't it? Now the next is here with the help of this definition. Now let us derive the expression for the magnetic potential at any point on the axial line of a dipole. Now let us see here. I think that this derivation, you may not feel any difficulty in understanding this one, because the way in which the electric intensity at any point on the axial line, we have discussed it in the same manner, this also be, isn't it? Now here, all of you carefully you will see here, first on the axial line, on the axial. Now let us consider this is a magnet or magnet, north pole, and this is the south pole. The distance between these two, it is called as the magnetic length. Usually we take it as 2L, and this is the center. Now the axial line is what? Yes, you are very familiar that it is a straight line passing through the poles and the center of the magnet. Then this is the center, and these are the poles. A straight line passing through this, it is what is the axial line. Okay. Now take any point, what is the P on the axial line, then this point P is at a distance of D from the center of the magnet. Now, here one more point I want to make it clear. Since the poles, North Pole and South Pole are unlike, then the potential and the North Pole is taken as positive, whereas the South Pole is taken as a negative. Since the North Pole is positive, South Pole is negative, therefore the potential due to the North Pole is taken as positive and the potential due to the South Pole is taken as a negative. Now, when you consider this is the point P, which is at a distance of D from the center of the magnet, then at this point P, there are two potentials are acting. One is due to the North Pole, another is due to the South Pole. Now, see, remember that potential at any point formula is what? General formula 1 divided mu naught divided by 4 pi in M divided by, isn't it? M is what? It is a pole strength, and D is what? It is a distance of the point from the pole. It is distance of the point from the pole. Now, here this is a magnet, isn't it? Of length 2L, and the pole strength of each is how much it is the equal to M. Now, potential at P due to the North Pole, isn't it? Potential at P due to North Pole, N North Pole, that taken as the Vn is equal to, apply the formula, isn't it? Mu naught divided by 4 pi into M divided by distance of the point from the pole. This is the North. Now, again we can write this distance, it is equal to this distance minus of this one. Isn't it? That is, here this distance is D minus of, then this distance, this total distance is what it is the 2L. This distance, it is nothing but it is the L, minus of L. Next, same way, potential at P due to South Pole, due to this South Pole, that yes, it is equal to, isn't it? Then mu naught divided by 4 pi, this is M divided by, then again South Pole is here, then distance of this point from the South Pole is here. This total distance, you can take it as what? This distance plus this distance. That is here D plus what is the here. Now you have already had to do that. Potential due to the North Pole is taken as positive, whereas potential due to the South Pole is taken as what is the negative, so that here this will get minus. Now, the next is net potential at P. Net potential at P is, let's take this as V. Now listen here, one more point. Potential, it is a scalar quantity, isn't it? Yeah, you know that intensity or magnetic intensity, it is a vector. It has got magnitude as well as the direction. But whereas why I don't want to go again what is the of this, because already we have discussed it in the last class about this one. But the potential, it is a scalar. Then who will say that it is a scalar? Then this you can understand by going to its basic definition, isn't it? Then you must have this information also, isn't it? That is why the potential is a scalar quantity. It is that according to the definition, the potential at any point in the magnetic field, it is equal to what? Work done. Isn't it? Work done in bringing a unit not from infinity to the point. Potential is equal to the work done only. Now, since you are studying that in lower classes, work done is a scalar quantity, isn't it? So that since the potential is equal to the work done, therefore work done is scalar, therefore potential is also being a scalar, isn't it? Then whereas the intensity is equal to what? Intensity at any point is equal to the force acting on a unit pole at that point. Therefore, since the force is, that means field, it is equal to the force. Therefore, since the force is a vector, therefore field is a vector. But whereas in the potential, potential is equal to the work done. Work done is a scalar, hence the potential is also being a scalar. Therefore, net potential is equal to, when it is a scalar quantity, just you have to what is sum up. If you want to find the resultant, then you add them. That nothing but here, whichever quantity is positive, that you take it as a plus, and the quantity which is negative, that you take it as a minus. Now here, potential due to the north pole is positive, potential due to the south pole is a negative, hence the net potential it is equal to then potential due to the north pole plus potential due to the south. This is. Now potential due to the north pole is this much, that is mu naught divided by 4 pi m divided by d minus of L is a minus, because the potential due to the south pole is negative, minus of what we get it here, mu naught divided by 4 pi m divided by d plus L, isn't it? Now what you do is you take out the common factor, is it a mu naught divided by 4 pi m is a, what is the common? Now the remaining is 1 divided by d minus L minus 1 divided by d plus what is the L. Now this is equal to mu naught divided by 4 pi m, I will take as it is. Now LCM is, what it is the product of this is LCM, that is d minus L into d plus L. Now here we will get d plus L, isn't it? Now this is minus, it is what we get here, d minus of L. Now this is equal to what we get, mu naught divided by 4 pi m into, this is nothing but it is d square minus a plus b, a minus b form. Therefore, you will get a square minus b square. Then here in the numerator, d plus L. Apply the minus sign here, minus d, minus of minus will get here plus. Like now, what will happen is this plus d and minus d will what will gets cancelled. Now, what we left here, it is equal to, I will write here. Now this value, it is equal to, it comes out mu naught divided by 4 pi, is it? L plus L is what we get here, 2L into m, is it? That directly right here, then this is 2L into m divided by d square minus L. And next, this is equal to, this is the constant that I will read as it is, mu naught divided by 4 pi. And yeah, you know that the product of the pole strength and magnetic length, it is nothing but equal to the magnetic moment, isn't it? Now this is equal to m divided by what we get here, d square minus l square. Now so this is the formula, isn't it, of the potential at any point on the axial line of a dipole, isn't it? Now again, when you apply for what it is the in case of a what is a short magnet, isn't it? Now I think this all of you might have understood, isn't it? Now I will erase this one. For a short magnet, what we did here, for a short magnet, L is, isn't it, very much less than d. Length of the magnet is small as compared to the distance. Now, in that case, this is V is equal to mu naught divided by 4 pi. This is m divided by d square minus l square, which is same. Now, this we can write it here as mu naught divided by 4 pi. Isn't it? Next, m we read as it is divided by d square we take out. Isn't it? D square. What we get here, 1 minus of L square divided by D square. Now, what will happen is, we are already, this type of the cases we have discussed in finding the formula for the intensity, that since L is very much less than D, therefore, this L value is in the numerator, which is very, very small as compared to D, this factor is almost equal to 0. Now, when it becomes approximately 0, that is here L square divided by D square, it is approximately isn't it? Therefore, what is the value we get it here? V is equal to, it is mu naught divided by 4 pi, isn't it? Now this is m divided by what we get here is a d square minus divided by d square. This is 0, isn't it? Therefore, you will get only d square. Now see, this is the formula of the potential, isn't it? Along the axial line of a what is short line. Then in general it's this one. That means I have already made it clear that when you have to use this formula and when you have to use this formula, mean see, if the magnetic length it is given to you, L value is given to you, then you have to take this one. Suppose if it is L value is not given, then it is understood that it is what a short magnet. Then in such cases you have to use this formula. And if by using this formula very easily you can calculate it. Then in this case the factors are, this is a constant, mu naught by 4 pi is equal to 10 raised to minus 7. M is nothing but what? It is a magnetic moment, is it, of the dipole, and D is what? It is the distance of the point from the center of the dipole. Okay. Now, by using this formula or that formula, you can calculate what is the magnetic potential. Now, see, this is about the potential or magnetic potential at any point on the axial line of a dipole. Isn't it? Now, after studying this one, now let us go to the next one. That is, what is the formula of the magnetic potential at any point on the equatorial line of a dipole? Here on the what is the equatorial line? Equatorial line. Yes, already you are familiar that to be correct as an equatorial line is, now for example this is a bar magnet. This is the north pole and this is the south pole. Isn't it? This is the center of the magnet. Isn't it? Then equatorial line is what? It is the line. Isn't it? Passing through the center of the magnet and perpendicular to its length. That line is known as what is the equatorial line. Now here, this is a line. Isn't it? Passing through the north and south poles, and the line passing through the center perpendicular to the what is the length of the magnet, isn't it? Now, this is called as the equatorial line. Now, you take any point, is it a P on the equatorial line, which is at a distance of D, is it a, from the center of the magnet, isn't it? Now, this center of the magnet, let us consider. Now, again, here, at this point, there are two, what is the potentials are acting, isn't it? Then, one is potential due to the north pole and another is potential due to the south pole, it is there. Then this is the potential due to the north pole and potential due to the south pole. Then therefore, first we calculate what is the potential due to the north pole and what is the potential due to the south pole. Then here, now you join this one, isn't it? This. Now again, the pole, strength of the pole is equal to how much we take it? Strength of the pole is equal to isn't it? Then P is a point which is at a distance of D from the center of the magnet. Then here potential at P due to north pole N pole Vn, it is equal to, the general formula is what? The general formula is mu naught divided by 4 m small m divided by this formula is what? Distance of the point of the pole. Potential at any point due to a what is a magnetic pole, already I have given to you, mu naught by 4 pi into m small m it is divided by, you will get distance of the point from the pole. Now, this is the point and this is the pole, then this distance it is equal to, we write it here as NP, isn't it? Then this is next potential at P due to south pole, isn't it? South pole, this you take it as Vs, it is equal to, then what we get here is equal to, then mu naught by 4 pi, this is as it is, and this m divided by distance, isn't it, of this point from this south pole. Now this you can write it here as what is the SP, isn't it? This is but this is negative. And south pole potential due to the south pole is negative. Now net potential, isn't it? Net potential at P is equal to Vn plus what is the distance. Now you can see that in this case here, when you apply or when you look at the formulas of this one, in this case and in this case, this is same, isn't it? This also is same. NP and NS. But you can see that here in this particular case, NP is equal to what it is the, isn't it? NP is equal to NS, so that what will happen is then this value is, when you write it here as mu naught divided by 4 pi, isn't it? M divided by NP minus mu naught divided by 4 pi M divided by SP. Therefore, this is the same for this and this only, this one, then here NP is equal to NS, isn't it? Distance is same. This distance is equal to this distance, so that this value, this is and this is same is what? Even both are equal means what? Then here also you can write it here as NP, SP. Then, but here since NP it is equal to NS. Now, what is here? This also you write it as what it is the NP. Then what will happen is this will be same, will get cancelled. Therefore, is it? Then net potential is it? Therefore, net potential at P is what it is of V is equal to 0. Net potential at P, that is V is equal to this much. Now this is equal to 0 because we are saying the distance is same, isn't it? So that this value is equal to this value. Hence, one is positive, another is negative, so that you will get what it is a 0. Then this shows that not only here, wherever you take it, at any point on the equatorial line, isn't it? Then this distance is equal to this distance. That is everything it is same. Only the distance, if it is variable, potential is also be variable. When the distance is same, then potentials are also the same. Either you take it here, anywhere, then this distance is equal to this distance is equal to this distance, so that then potential due to this and due to this, they are equal and opposite, hence they cancel each other. That means wherever you take it, at any point on the equatorial line, then potential is 0, isn't it? So that the another way is what we say is equatorial line is the line of what is the 0 potential. This you can define like this also. The equatorial line is the what it is the line of 0 potential. That means on the equatorial line, wherever you take it, the potential will become equal to 0. Now see, these are the what it is the that is the formula. It is not a because the potential is what is the 0 net potential. But whereas on the axial line, isn't it? You are having the formula for the potential, isn't it? Now, after understanding these two, what is the derivations of the magnetic potential at any point, isn't it? Due to a dipole on the axial line and the equatorial line, isn't it? These two we have what is the distance. Now see, after understanding this one, isn't it? Now let us come to the next point, that is nothing but it is the During the discussion of this one, electric field, electric intensity, and what is the magnetic potential and all, then one factor we come across, that is here, for example, when you take in potential at any point, mu naught divided by 4 pi m divided by d, isn't it? Then here, this mu naught, it is nothing but what? Mu naught, we have called it as the absolute permeability. Are you following? Now, first of all, absolute permeability means what? It is the permeability of air or vacuum. It is known as the absolute permeability. Now, let us try to understand what actually the meaning of the permeability, isn't it? Now, here, let us try to understand this definition first. Permeability. Now, what is the meaning of the permeability? Now, first thing is, now in the very first class we have discussed that the magnets are of two types, isn't it? The permanent magnet, isn't it? And second is the non-permanent magnet, isn't it? Permanent magnet means which one? It is bar magnets, what you are having, they are permanent magnets, isn't it? And the non-permanent magnet, we have taken it as a what is the current carrying loop. Isn't it? It is one of the examples of non-permanent magnet, because in the loop, isn't it? If there is a current, then it acts like a magnet. If there is no current, then it will not act like a magnet. One, isn't it? And second is, even there are certain materials are there, certain materials, isn't it? Like iron is there, that is called as a ferromagnetic material. Now, that ferromagnetic material, initially it, what is the, not a magnet. Initially it is not a magnet, but it can be converted into the magnet, isn't it? How to convert it into the magnet, isn't it? That what is the iron ferromagnetic material, which is not a magnet, that can be converted into the magnet by placing it in a magnetic field, isn't it? Now, let us consider this is a piece of iron. Now, it is not a magnet, isn't it? But you can convert it into the magnet. How? What is, you take this iron piece and place it in the, this is the magnetic field, like this one. And in this magnetic field, you put this one. Now, it will become as a magnet. It is, when it becomes as a magnet to some extent, then what will happen is this, what is the material, it is allowing what the magnetic lines of forces to pass through it. This material, when it is placed in the magnetic field, then this material, what it will do? It allows for what? To pass the magnetic lines of forces, isn't it? It allows the water to pass the magnetic lines of forces, isn't it? Then, in the previous classes, that is in the lower classes, you have studied in detail regarding what is the magnetic line of force, electric line of force in electricity, magnetic line of force in the magnet, isn't it? What are the properties of the magnetic lines of forces? They never intersect, that they, all these points you have studied in detail, isn't it, in your lower classes. Then I don't want to go about that, isn't it? Now, just you remember that any material, isn't it, which is not a magnet, it can be converted into the magnet by placing it in a magnetic field, isn't it? Now, when it is placed this material in a magnetic field, then what will happen is this material, it allows for what? To what is the pass the magnetic lines of forces. Then what will happen is the ability of the material, isn't it, to pass the magnetic lines of forces, that ability, it is known as what is the permeability. That means, listen here, the different materials have different ability. Ability in what? Ability in allowing the magnetic lines of forces through it. Then some materials are having the more ability. Then we say that permeability is more. If the material has got less ability to allow the magnetic lines of forces, then we say that its permeability is less. For example, when you take the iron piece, that is a ferromagnetic material, then it has got the more ability to pass or more ability to allow to pass the magnetic lines of forces than the steel, etc. Isn't it? Therefore, that is, you remember that the different materials have different ability, isn't it? Ability in what? Ability to allow the magnetic lines of forces to pass through it. Then that ability is known as what? The permeability. Now, once again, is it a? I repeat the definition of the permeability. What means? Permeability of a material is its ability to allow the magnetic lines of forces to pass through it is known as the permeability, isn't it? The different materials are having the different ability, isn't it, to allow the magnetic lines of forces. Hence, the different materials have the different permeability, isn't it? Now, this is the definition of what is the permeability. And next, coming to the what is the one more point, that is, but it is the susceptibility. Susceptibility. Then, regarding this susceptibility, also you have studied, isn't it? And in not only in physics, even in chemistry also you have come across these what are the definitions, isn't it? I don't know how many of you are still remember those definitions, even though you have studied in your lower classes both in physics as well as in chemistry also, isn't it? Now, when I saw some of the what is the chemistry books, isn't it? There I find that then there is one topic is there regarding the diamagnetic material, paramagnetic material, ferromagnetic material, even in what a chemistry, isn't it? There you will find these definitions, permeability, susceptibility, etc. But to what extent you have understood that, isn't it? Now, let us try to understand regarding this what is the susceptibility. Then, what is the meaning of the susceptibility? Now, before going to the definition of this one, isn't it? Whatever the basic points are required, let us try to understand, isn't it? The first. Now, here just I made it clear. Any material which is not a magnet that can be converted into the magnet. How? By placing it in the magnetic field, isn't it? Then I have given an example that the iron piece, isn't it? Now this is not a magnet now, isn't it? That can be converted into the magnet by placing it in a magnetic field. Now this is what is the magnetic field. Now you place this material into the magnetic field B. Now this material, when you place it here, it is converted to the magnet. One. Next thing is that if it is converted into the magnet means to what extent it is converted into the magnet. That means, is it the complete material is converted into the magnet or partially converted into the magnet? Isn't it? How it is? Isn't it? Then you should have a clearer concept, isn't it? That if this is a material which is not a magnet, isn't it? It can be converted into the magnet by placing it into the magnetic field. Then as you place this material into the magnetic field, isn't it? It doesn't mean that this complete material, it is what it is, may be completely converted into the magnet or partially also, isn't it? Then to what extent it is converted into the magnet, isn't it? Whether it is completely converted into the magnet or partially what it is converted into the magnet, it depends upon which factor means. It depends upon one thing, what it depends upon the applied magnetic field. How much magnetic field you apply. If you apply the more magnetic field, then this material is what is converted more into the magnet. Or we use the word that is magnetized. Magnetized means what? converted into the magnet. Isn't it? Whether this material is what is the more magnetized or less magnetized, it depends upon the applied magnetic field. One. Second factor, it depends upon the nature of the material also. It depends upon the nature of the material, isn't it? Then which type of material you have placed it. Then just now I have given an example that iron, isn't it? Now when you take the iron, very easily converted into the magnet, isn't it? You don't require magnetic field to convert completely into the magnet, isn't it? But at the same time, instead of taking the iron, when you take it, what is a steel, but it is not converted what it is easily. Isn't it? You require the more and more field, magnetic field, to convert completely into the magnet. Are you following this one? That means when any material is placed into the magnetic field, whether it is more magnetized or less magnetized. That means whether it is more converted magnet into more or less. That is the word we use it as a magnetized. Whether it is more magnetized or less magnetized, it depends upon the two factors. One is what it is depends upon the applied magnetic field, or sometimes we use the intensity of the applied magnetic field. Intensity of applied magnetic field. And second is what it is the nature of the material. Nature of the material. Example, the iron is very easily converted to the magnet, isn't it? Than the what is the steel, nickel, etc. This one. Now, this shows that, carefully listen here, when the different materials are placed into the same magnetic field, then the different materials are magnetized into the different extent, isn't it? Now, its meaning is that let us consider this is the iron, and other you take it as what is the steel, isn't it? This one. Now you place these two into the same intensity of magnetic field. This is the magnetic field of intensity H. Now you place this one here and this also. Now see, even though this is the iron and this is what it is the steel, it is an alloy, isn't it? Now, then, even though these two are the different materials placed in the same what is the magnetic field, but we see that iron is more magnetized and steel is less, isn't it? Then why it is? Because of their properties, isn't it? Property of iron and property of steel, it is different. Because of that, what is having their own property, and isn't it? That property, it is known as susceptibility. What it is? Why the different materials are placed into the same magnetic field? The different materials are magnetized into different extent. It is magnetized into the different extent. It is because of their own property, and that property it is known as what it is, a susceptibility. It is known as the susceptibility, isn't it? Then the next is here. This is the basic definition, isn't it? Or physical definition. Once again, I repeat here. Then when the different materials are placed into the same magnetic field, the different materials are magnetized into the different extent because of their property. That property is known as what it is, a susceptibility. This is the physical definition. And the mathematical definition is, yes, I had told you that this one, that is when the material it is placed into the magnetic field, then it is what is converted into the magnet. Whether the material is what it is, more magnetized or less magnetized, isn't it? Depends upon the applied magnetic field. One depends upon what? Applied magnetic field. If you apply the more magnetic field, then it will be more magnetized. If it is less magnetic field you apply, then it will be less magnetized, isn't it? Next. Then to what extent, try to understand the words here. to what extent the material is magnetized, isn't it? To what extent material as magnetized is measured in terms of what? It is measured in terms of what is the magnetic moment. It is measured in terms of magnetic moment. Now here, when you place any material in a magnetic field, then what will be? It is magnetized. It is more magnetized or less magnetic, depends upon which factor means. It depends upon how much magnetic moment it gains after placing it into the magnet. Whether it is what the more magnetized or less magnetized is measured in terms of what? It is measured in terms of how much magnetic moment it gains after placing it into the magnetic field. Then if it gains more magnetic moment, is it a? Then you see it is more magnetized. If it gets less magnetic moment, is it a? What it is the less magnetic? That depends upon the factor of what it is the H. Then if you are applying more H, listen here, if you are applying more H, then material gains more magnetic moment, hence we say that it is more magnetized. When the value of H is less, then the material acquires or gains less magnetic moment, then we say that it is what it is the magnetized less. Isn't it? So that here, how much magnetic moment it acquires depends upon that only we measure to what extent it is magnetized. Isn't it? If it is more magnetized, magnetic moment is more. Isn't it? If it is less magnetized, it gains less magnetic moment. Depends upon the value of H. Isn't it? Now, this magnetic moment, how much it is gaining, depends upon the value of H. Isn't it? Then it is directly proportional to what is the H it is. If you apply more H, it gains more magnetic moment, directly proportional, hence we say that it is more magnetized. If you apply less H, then it acquires less magnetic moment, then we say that it is a less. If magnetic moment, it is directly proportional to the intensity of the applied field. Now, mathematically, in order to remove this, what is the proportionality, we will put some constant. That constant, it is represented by, isn't it? This X type, but it is pronounced as what is the chi. This is what this one. Right. Then this is what chi. Now this what is the chi is a constant. That is pronounced as what it is pronounced as chi, and this is nothing but it is the susceptibility. X is what is the susceptibility. Susceptibility. Now, from this, what is the equation? Is it? Now, you can write this chi as how it is. This chi is equal to then m by what? Is it? M by. Therefore, what is the mathematical definition of the susceptibility? Is here. The susceptibility of a material it is equal to what? It is equal to the ratio of the magnetic moment acquired by the material. Magnetic moment gained by the material to the intensity of the applied field. Once again, repeat here: susceptibility of a material it is equal to the ratio of the magnetic moment gained by the material to the intensity of the applied field. That is a constant, and that constant it is called as the susceptibility. Now, once again, repeat here. First thing is, when the different materials are placed into the same magnetic field, the different materials are magnetized into the different extent. It is because of their property. That property is known as the susceptibility. This is the physical definition, isn't it? And mathematical definition is that the susceptibility of a material it is equal to the ratio of what magnetic moment, what is gained by the material to the intensity of the field. Now see, these are the two important definitions. One is what the permeability, and second is what it is the susceptibility. Now, once again, I will repeat these two definitions. What is the permeability? It is the ability of the material to allow the magnetic lines of forces to pass through it is known as the permeability. Next, susceptibility. In the susceptibility, there is a physical definition and the mathematical definition. What is the physical definition? Physical definition is that the when the different materials are placed in the same magnetic field, the different materials are magnetized into the different extent because of their property. That property is known as the susceptibility. And the susceptibility of a material is equal to the ratio of the magnetic moment acquired by the material to the intensity of the applied field. This is what is the susceptibility. Now, these are the two definitions, isn't it, connected to this one, isn't it? Now, I hope, isn't it? Now, we have discussed in this particular class about what is the magnetic potential is what, then what is the formula of the magnetic potential at any point on the axial line of a dipole, next on the equatorial line of a dipole, isn't it? Then you are having the formula for magnetic potential at any point on the axial line of a dipole. But whereas the potential at any point on the equatorial line is zero, and hence it is that line which is known as equatorial line is the line of zero potential. Next two definitions are, one is permeability and another is the susceptibility. And you know what is the meaning of the permeability and what is the susceptibility. I think now I will stop here. The remaining points we will discuss in the next class. Thank you.